So far, we have discussed much about the concept of entropy. I hope that through these sessions, you have become better acquainted with the concept of entropy. We have seen that it's such a chief or such a supreme quantity, physical quantity, which has got multiple roles, which has got multiple interpretations, which in a way we can say that is more important than many other physical quantities that we usually use to discuss in physics or thermodynamics, because this entropy actually helps us to predict even the direction of a process, whether or not a process will occur spontaneously or naturally, or whether or not certain process can occur in principle. Hope you remember you became aware of, or you heard about the concept of entropy in your lower classes, where entropy was always defined as a measure of disorder. Wherever we discussed entropy in lower classes, we always related entropy with disorder. Now let us try to understand in what way entropy is interpreted as a measure of disorder, or what actually is the meaning of the word disorder. I hope you remember in the beginning of our discussion of this module, I told you that entropy is one of the concept that is highly misunderstood or not clearly understood in physics, and our attempt is to make the concept more and more clear. I don't know whether you are getting the concept more clear, or at least your confusion is getting increased. And usually it is said, if you cannot convince somebody, confuse him. So certainly that is what is happening in whenever we begin to talk about entropy, because entropy is such a concept that has to be understood by contemplating on the concept beyond the mathematical symbols that makes it demanding. But we can do that. So our aim is to understand how entropy is related to the disorder. One thing I want to caution you is that the word disorder that is usually associated with entropy actually we do not mean in physics the physical disorder. So what we mean by disorder in entropy is the thermal disorder. So we can say in a way that entropy of a system can be regarded as the measure of its thermal disorder, or the better word, because since we are not the native users of English language, many words that is used by the native users of the language, we misinterpret it. One of the best example is the word disorder. So by disorder, the proponents of the thermodynamics meant like Clausius, or it is Boltzmann, whoever it is, what they understood is the meaning of randomness. What is mean randomness? Means the ways of arranging something. If it is more, if you can arrange a system in more number of ways, we can say that there is more randomness in the system, or more disorder in the system. Or I hope you remember the Boltzmann's expression for entropy we have discussed in previous sessions. S is equal to KB log omega or W. So this particular thing, quantity W is known as the thermodynamic probability. So you can see that entropy is related to log of a quantity which is known as thermodynamic probability. Don't confuse the word thermodynamic probability. Actually, W stands for the randomness of the system, and W is known as the number of microstates. I will discuss about this one in detail when we go to the module number 5, statistical mechanics, where it will be derived if not completely discussed. Number of microstates accessible to the system. So a system having greater entropy will have more number of microstates which can be accessed. അതായത് ഒരു സിസ്റ്റത്തിന് വ്യത്യസ്ത തലങ്ങളിൽ അല്ലെ വ്യത്യസ്ത രീതിയിൽ ആ സിസ്റ്റത്തിന് അച്ചീവ് ചെയ്യാൻ പറ്റുന്നുണ്ടെങ്കിൽ if the system can attain a large number of microstates within a given constraint, we will call that its entropy is small. അപ്പോൾ ഇവിടെ ഡിസോർഡർ എന്നുള്ളതുകൊണ്ട് ഉദ്ദേശിക്കുന്നത് what we mean is the thermal disorder. ഓക്കെ, ഒരു സിസ്റ്റത്തിൻ്റെ പാർട്ടിക്കിൾസിന് അസംഖ്യം വ്യത്യസ്തമായ സ്റ്റേറ്റുകൾ സ്വീകരിക്കാനുള്ള ഒരു അവസ്ഥയാണുള്ളത് എങ്കിൽ നമ്മൾ പറയും ഇറ്റ് ഹാസ് ഗോട്ട് ഗ്രേറ്റർ തെർമൽ ഡിസോർഡർ. Okay, and actually in a broad sense now we relate entropy with the loss of information. ഒരു സിസ്റ്റത്തിൻ്റെ എൻട്രോപ്പി കൂടുതലാണ് എന്ന് പറഞ്ഞാൽ ആ സിസ്റ്റത്തെക്കുറിച്ച് നമുക്കുള്ള പ്രെഡിക്റ്റിവിറ്റി കുറഞ്ഞു വരുന്നു എന്നാണ് അർത്ഥം. എൻട്രോപ്പി കൂടിയ ഒരു സിസ്റ്റം എന്ന് പറഞ്ഞാൽ ആ സിസ്റ്റത്തെ പറ്റിയുള്ള നമ്മുടെ പ്രെഡിക്റ്റബിലിറ്റി, അതിൻ്റെ സർട്ടൈനിറ്റി വല്ലാണ്ട് കുറഞ്ഞു വരുന്നു എന്നാണ് അർത്ഥം. സോ യൂഷ്വലി ഇൻ എ ജനറൽ സെൻസ് നമ്മൾ പറഞ്ഞു ഫിസിക്സിൽ എൻട്രോപ്പി എന്നുള്ളൊരു കോൺസെപ്റ്റ് ക്ലോഷ്യസ് ഇൻട്രൊഡ്യൂസ് ചെയ്തതിന് ശേഷം ദ വേർഡ് എൻട്രോപ്പി ഹാസ് ബിക്കം യൂണിവേഴ്സൽ. നൗ ഇറ്റ് ഈസ് യൂസ്ഡ് ഇൻ philosophy, it is used in information science, it is used in theology, it is used in metaphysics. എല്ലായിടത്തും ഉപയോഗിക്കുന്ന ഒരു വാക്കായിട്ട് മാറിയിട്ടുണ്ട് എൻട്രോപ്പി. ഓക്കെ, ആൻഡ് ഇൻ ഈച്ച് ടോപ്പിക് എൻട്രോപ്പി ഹാസ് ഗോട്ട് സ്ലൈറ്റ്ലി ഡിഫറെൻറ്റ് മീനിങ്. ഇൻഫർമേഷൻ സയൻസിൽ എൻട്രോപ്പി കൂടുതലായിട്ട് ഉപയോഗിക്കുന്നുണ്ട്. വെയർ എൻട്രോപ്പി ഇൻ ഇൻഫർമേഷൻ സയൻസ് ഈസ് ആക്ച്വലി ലോസ് ഓഫ് ഇൻഫർമേഷൻ. ഓക്കെ, ലോസ് ഓഫ് ഇൻഫർമേഷനെയാണ് സാധാരണഗതിയിൽ മോർ എൻട്രോപ്പി എന്നാണ് ഉദ്ദേശിക്കുക. ദറ്റ് ഈസ് എ തിയറം നോൺ ആസ് ഷാനൺസ് എൻട്രോപ്പി എന്ന് പറഞ്ഞിട്ടൊരു എൻട്രോപ്പി തന്നെയുണ്ട്. ഇതൊക്കെ നിങ്ങൾ എവിടെയെങ്കിലും കേൾക്കുകയാണെങ്കിൽ ജസ്റ്റ് ഒന്ന് ഓർത്തിക്കണം ഞാൻ പറയുന്നുള്ളൂ. എൻട്രോപ്പി ഈസ് നോട്ട് എ കോൺസെപ്റ്റ് ദാറ്റ് ഈസ് നൗ ലിമിറ്റഡ് ടു thermodynamics. It has grown beyond. Okay, it has become so dear to many branches of science and arts, so that it has lost its original meaning. What we usually use in thermodynamics. So in a way we can say that entropy of the system is a measure of its thermal disorder. For example, you can if you consider the different phases of or different states of matter of the same matter. Okay, for example, say water you are taking. So water can be solid state like ice, or it can be liquid water, or it can be the vapor, right? Specifically speaking, we will say usually the entropy of solid state is usually less than that of the liquid state, which is still less than that of the gaseous state. That is, the solid state is the most ordered, we know that. Okay, from the crystallographic information or molecular information also, you know that the solid state is more ordered, the liquid state is less ordered, and the gaseous state is the least ordered amongst the three phases of matter for a particular substance. Okay, and automatically we have seen that, or we have seen that you have a solid, you give some heat energy, it can get converted into liquid, right? So solid to liquid conversion can happen. So the solid to liquid conversion, when it happens, we call it as melting. There is what is known as latent heat. Okay, latent heat is involved. So similarly, liquid to vapor also can happen. There is some latent heat of vaporization involved there. So you know that whenever there is a latent heat involved in a transformation or a phase transition, the temperature of the substance doesn't change. So automatically there was a question like, what actually is this latent heat being used to? Where the heat given to the system goes? Okay, you have got ice at 0 degrees Celsius, you give some heat to it, Q amount of heat is given to it. Okay, you know that as long as the entire ice is not getting converted into liquid state, the temperature of the sample will not change. It means that even though you are giving heat, the temperature is remaining constant. So the question goes like, where actually this heat is being used. So we usually say that it is being converted into the latent heat, and actually where is this latent, what is the use of. So you can see that in such phase transition, the latent heat is used for increase of entropy. So this is something very, very important concept in such phase transitions. So wherever the phase transitions in which a latent heat is involved is usually known as first order phase transition. So there is a classification of phase transition into first order and second order phase transition. You will learn about it later. So in first order phase transition, a latent heat is usually involved. So in such phase transitions, where is that heat energy going? It was actually a mystery. So now it is understood that this latent heat is used in the increase of entropy. And from the previous discussion, we have seen that with increase in entropy, the increase of the available or useful energy, will be going on reducing. So with the increase in entropy, since the available energy decreases, it will not be resulting in an increase in the temperature. So latent heat is used for the increase of entropy in all first order phase transitions. So that is one thing that you have to connect. There are several other examples of to show how entropy is related to disorder. One such example is free expansion. So in free expansion there is no any heat transfer, but it is able to, because it happens in adiabatic enclosure. So during free expansion also the entropy of the system increases, because you can see that during free expansion the volume increases. Expansion is volume. There is no heat exchange, no heat exchange. But even then, by the removal of a partition, the volume increases. So as the volume increases, the particles will get more space to move in. So what about the predictability about the particular state of the system? Won't the predictability will be getting reduced? Because I will say that the randomness have got increased. The molecule earlier was confined to very small volume. Now the molecule can be anywhere. So you cannot predict exactly where a particular molecule will be if the volume has increased. So we will say that the disorder has increased, molecular disorder has increased, or thermal disorder has increased, even in the absence of heat. So we can say that there is entropy can be related to disorder. More the volume, more will be the disorder. Or you consider another phase transition, which is known as from the ferromagnetic phase to the paramagnetic phase of a magnetic sample. You know that ferromagnetic samples we have discussed, like iron or something, which is characterized by the presence of magnetic domains. So you learned about this one, the presence of magnetic domains in what is known as ferromagnetic sample. So there are magnetic spins oriented in different directions. There are certain regions of short range order, what we call as the ferromagnetic. What I am drawing as arrows is magnetic spins, magnetic moments. So this is the characteristic of a ferromagnetic substance. And you know that if you increase the temperature, of a ferromagnetic substance, so this is ferromagnetic substance, above a temperature what is known as Curie temperature, which is a transition temperature, the ferromagnetic substance will become what is known as a paramagnetic substance. You have learned about it in magnetism, right? So a paramagnetic substance. So you know that in a paramagnetic substance, the magnetic dipoles will be oriented in random directions. So you can see that what happens in this transition. So with the increase in temperature, beyond the temperature, the more ordered, this one, ferromagnet is more ordered, because there was a short range order in magnetic domains. More ordered ferromagnetic substance will be getting converted into less ordered paramagnetic substance. So you can see that in this case also, we'll say this ferromagnet is having usually lesser entropy, and S ferromagnetic is lesser entropy compared to S paramagnetic. The reason, because we can say the magnetic order, in the magnetic dipoles is getting what? Reduced, or disorder will be increasing. So this is the way. So, and one thing more, we have seen that the equilibrium is a state of maximum entropy. Equilibrium is a state of what? Maximum entropy. And systems will tend to move from lesser equilibrium state to more equilibrium state. Means what? Actually, what is the tendency of the system? In terms of entropy, we can say that systems tend to move towards increasing entropy. Remember? So the equilibrium is a state of maximum entropy. So during the process of attaining equilibrium, every system is actually trying to maximize its what? Entropy. Maximizing entropy means the randomness of the system will be getting maximized. Randomness of the system will be getting maximized, or the number of accessible microstate for a system will be highest in the equilibrium state. And we have seen in all natural process, including living process, which is whether it is growth or decay, there is always a transition from an ordered state to the disordered state. So everything is moving towards a higher disorder. Disorder, okay, means randomness. So actually it is nothing but the principle of increase of entropy. So this is a way in which we usually relate with disorder. Okay, and the concept has become so common that usually people have even related, started to relate entropy in everything, even in daily life. Like usually people say that even though it is not scientific, but people usually say that a successful person is one having lower entropy. Okay, successful person is one having lower entropy. Lower entropy means better order. So a person will be keeping everything in place, right? And it's easy to just recover what he has kept, because he is keeping order, means his life is having lesser entropy. Compared to a person who is having more entropy, means he will not be keeping any just things in order. So if he has to search for something, whatever is in order, he has to make it more and more disorder. So his entropy will be going on increasing. So that is actually just telling about the relation of entropy with the disorder. But it's not the physical way in which we discuss disorder in thermodynamics. Remember, in thermodynamics, entropy of the system is regarded as a measure of the thermal disorder, okay, or the randomness. The better word is it's a measure of randomness of the system, okay, and greater the entropy, lesser will be the predictability of the particular system regarding its thermodynamic properties. Okay, that's there. Now there is another before we end up the session, let me discuss one more thing. Another important concept, that is the concept of heat death of the universe. Heat death of the universe. You know that universe here means the physical universe. See, what is the concept of heat death? See, we have learned about the origin of the universe, right? There are several theories regarding the origin of the universe, and one of the most established theory being the Big Bang theory, right? Okay, universe originated out from what is known as a singularity, okay, a point of infinite density following a explosion along with or accompanied by a sudden expansion, okay, causing a Big Bang, okay, right? Now, there are several theories regarding how the universe will finally end up, how the universe will finally end, what will be the fate of the universe. Fate of the universe means what will be the thermodynamic fate of the universe. That's what we discuss. See, one of the proposed theories regarding the fate of the universe is by considering a stage what is known as heat death. So by heat death, you have to understand this, one of the proposed fate, okay, and the avastha, end stages of the universe aayitana heat death. So what is the meaning of heat death? Let's see. As a result of every natural process which is inherently irreversible in its nature, there will be a continuous increase in the entropy of the universe. As we have seen that ds of the universe is always greater than or equal to 0, and this equal to 0 is for reversible process. Natural processes are irreversible, so entropy of the universe goes on increasing. So what will happen? And also we have seen that more the entropy of the universe, lesser will be the amount of available energy. Is it not? So as the entropy of the universe increases, available energy for conversion into useful work by a heat engine will be going on what? Decreasing. So available energy for conversion into work will be getting what? Decrease with the increase in the entropy. Ultimately, it is predicted, or we can just presume, that universe will be reaching in a state of maximum entropy as the time proceeds. Okay, the entropy of the universe goes on increasing and increasing and increasing, and until it reaches eventually a state of maximum entropy where there will be some uniform distribution of temperature, and what will happen is that heat will cease to flow, because the heat flows on account of temperature difference. So if see that you are continuously drawing heat from higher temperature to lower temperature, so from higher temperature to lower temperature, the heat spontaneously flows. So automatically what happens that if all the heat is getting lowered, okay, or if the temperature is getting lowered for all the heat reservoirs, finally what will happen, the universe will be having just uniform distribution of temperature, and the entropy will be going on increasing. The entropy of the universe will be going on increasing, and finally there won't be any temperature difference between any two points of the universe, and heat will cease to flow. So once there is no chance of heat flow, what will happen? There no more work can be acquired. No more work can be acquired from heat transfer or by using heat engines. So if you cannot have a heat engine to work, means it's some kind of situation. The same kind of situation arises for other forms of energy like mechanical energy or electric energy also. Similar kind of a situation can arise as time proceeds. And if you cannot draw work, if you cannot obtain work, if you cannot use energy, it means if the quantity of the energy available in the universe is not good to make work, then you can say the universe is in effect dead. The universe is in effect considered to be dead, because there is no sign of work. You cannot make work anymore. So universe is effectively dead, thermodynamically dead, and that is what we call as the heat death. So heat death of the universe is one of the proposed end stages of the universe, in which heat ceases to flow, and you cannot obtain work. You cannot obtain work due to the increase in the entropy as a result of the natural process. Okay. Now there is another very interesting statement that you may come across while you read some books or sites. That is, this is a very catchy quote. Okay, maybe. See, entropy gives the direction of the arrow of time. Entropy gives the direction of the arrow of time. What is my arrow of time? Arrow of time means in which direction time is proceeding. Okay, സമയത്തിൻ്റെ ദിശ എന്ന് പറഞ്ഞാൽ ആരോ ഓഫ് ടൈം ഉദ്ദേശിക്കുന്നത് സമയത്തിൻ്റെ ദിശ. അപ്പോൾ എൻട്രോപ്പി നമുക്ക് സമയത്തിൻ്റെ ദിശ കണ്ടുപിടിക്കാൻ സഹായിക്കുന്നു. The meaning is that, suppose that you have got two snapshots of a system. This is a system. You take a photograph of the system. Okay, so you have got two snapshots of the system. So let me say that this is S1, same system at a time t1, and system one I can call. See, no, S1 is not okay, and I have got system. Let me name it as S better. No, system S, and we say that at a time t2. At a time t2, the same system, I'm denoting it as S dash to show that there is some change in the system. Let me say that S1 be the entropy of the system. S1 be the entropy of the system. We say that this is an isolated system, to be very precise. Isolated system. Okay, this is the same isolated system at some other time t2. So let me say that this is its entropy is S2. So S1 is the entropy of the isolated system at some instant t1, and S2 is the entropy of the system at some instant t2. Now if you want to tell that which time, t1 or t2, that was early, t1 or t2, which one was early, Okay, you are just given two photographs or means you are given some information regarding a system at some instant t1 and some other instant t2. You do not know which one was an early time. Okay, സപ്പോസ് ദാറ്റ് നിങ്ങൾക്ക് തന്നിരിക്കുന്ന ഫോട്ടോയിൽ ഇന്നലെ ഒരു സിസ്റ്റത്തിൻ്റെ ഫോട്ടോയും ഒരു ഐസൊലേറ്റഡ് സിസ്റ്റത്തിന് ഇന്നലെ എടുത്ത ഒരു ഇൻഫർമേഷൻ ഡാറ്റ സെറ്റും ഇന്നെടുത്ത ഒരു ഡാറ്റ സെറ്റുമാണ് നിങ്ങൾക്ക് ഫോട്ടോ എന്ന് പറയാൻ ഉദ്ദേശിക്കുന്നത്. ഐ ഡു നോട്ട് മീൻ ദ ഫിസിക്കൽ ഫോട്ടോ, മീൻസ് യു നോ ദ ഇൻഫർമേഷൻ ഓഫ് ദ സിസ്റ്റം യെസ്റ്റർഡേയ്സ് സ്റ്റേറ്റ് ആൻഡ് ടുഡേയ്സ് സ്റ്റേറ്റ്. അപ്പോൾ നിങ്ങൾ എന്ത് കമ്പയർ ചെയ്താൽ മതി, ആ സിസ്റ്റത്തിൻ്റെ എനർജി കമ്പയർ ചെയ്താൽ ഓക്കെ നമുക്ക് കാര്യമായിട്ട് പറയാൻ പറ്റില്ല, ബിക്കോസ് ഇറ്റ്സ് ആൻ ഐസൊലേറ്റഡ് സിസ്റ്റം, റൈറ്റ്? സോ നിങ്ങൾക്ക് കമ്പയർ ചെയ്യാൻ പറ്റുന്നത് എന്താണ്, ഈ രണ്ട് സിസ്റ്റങ്ങളുടെയും എൻട്രോപ്പി നിങ്ങൾ കമ്പയർ ചെയ്യുക. സപ്പോസ് ദാറ്റ് യു ആർ ഗെറ്റിംഗ് ദാറ്റ് S1 ഈസ് ലെസ് ദാൻ S2 എന്നൊരു ഇൻഫർമേഷൻ കിട്ടിയെന്ന് കരുതുക. യു ആർ ഏബിൾ ടു റീച്ച് എ കൺക്ലൂഷൻ ദാറ്റ് S1 ഈസ് ലെസ് ദാൻ S2. Okay, then you can conclude that T1 is an earlier time. T1 is an earlier time than T2, earlier to T2. I think you will be able to understand what is the meaning. Why we are able to conclude this one? Because of the second law of thermodynamics, which says that entropy of an isolated system will be always increasing, or it will remain what? Constant. ഓക്കെ, സോ എൻട്രോപ്പി എപ്പോഴും ഇൻക്രീസ് ചെയ്തുകൊണ്ടിരിക്കുന്നതുകൊണ്ട് തന്നെ എവിടെയാണോ ഏത് സമയത്താണോ എൻട്രോപ്പി കൂടുതലുള്ളത് അത് എന്തായിരിക്കും, ലേറ്റർ സംഭവിച്ചതായിരിക്കണം, കാരണം കൂടിക്കൊണ്ടിരിക്കുകയാണ്, റൈറ്റ്? അപ്പോൾ നമുക്ക് ടൈം ഏത് ദിശയിലാണ്, ടൈമിൻ്റെ ദിശ എന്നുള്ളതുകൊണ്ട് തെറ്റിദ്ധരിക്കരുത്, ഏതാണ് നേരത്തെ നടന്നത് ഏതാണ് ശേഷം നടന്നത് എന്ന് തിരിച്ചറിയണമെങ്കിൽ നിങ്ങൾ എന്ത് കമ്പയർ ചെയ്താൽ മതിയാവും, നിങ്ങൾ ആ സിസ്റ്റത്തിൻ്റെ എൻട്രോപ്പികൾ തമ്മിൽ കമ്പയർ ചെയ്തിട്ടുണ്ടെങ്കിൽ നിങ്ങൾക്ക് പറയാൻ പറ്റും ഇതിലേത് സിസ്റ്റത്തിൻ്റെ ഇൻഫർമേഷൻ ആണ് നേരത്തെയുള്ള ഇൻഫർമേഷൻ, ഏത് സിസ്റ്റത്തിൻ്റെ ഇൻഫർമേഷനാണ് അതിന് ശേഷം ലഭിച്ചത്. ഓക്കെ, അതുകൊണ്ടാണ് നമ്മൾ സാധാരണ ഈ ഒരു റിസൾട്ട് കൊണ്ടാണ് ഓക്കെ എൻട്രോപ്പി ഓൾവേസ് ഇൻക്രീസസ് എന്നുള്ള കോൺസെപ്റ്റ് കൊണ്ടാണ് ഇന്നലത്തെ എൻട്രോപ്പിയെക്കാളും കൂടുതലായിരിക്കും യൂണിവേഴ്സ് എടുക്കുവാണെങ്കിൽ. യൂണിവേഴ്സ് എടുത്തോളൂ, നിങ്ങൾ ഐസൊലേറ്റഡ് സിസ്റ്റം ഒഴിവാക്കിക്കൊള്ളുന്നിട്ട് ഇന്നലത്തെ യൂണിവേഴ്സിൻ്റെ ഇന്നലത്തെ എൻട്രോപ്പിയെക്കാളും എന്തുകൊണ്ടും ഇന്നത്തെ എൻട്രോപ്പി എന്തായിരിക്കും കൂടിയിട്ടുണ്ടാകും. നാളെ യൂണിവേഴ്സിൻ്റെ എൻട്രോപ്പി എന്ന് പറയുന്നത് ഇന്ന് യൂണിവേഴ്സിൽ എന്ത് എൻട്രോപ്പി ഉണ്ടോ അതിനേക്കാളും കൂടുതലായിരിക്കും. മറ്റന്നാളത്തെ എൻട്രോപ്പി നാളത്തേക്കാളും കൂടുതലായിരിക്കും. അപ്പോൾ തീർച്ചയായിട്ടും നിങ്ങൾ എൻട്രോപ്പി കമ്പയർ ചെയ്യുവാണെങ്കിൽ ഒന്നുകിൽ ഒരു ഐസൊലേറ്റഡ് സിസ്റ്റത്തിൻ്റെ കമ്പയർ ചെയ്യുക അല്ലെങ്കിൽ യൂണിവേഴ്സിൻ്റെ. ഓക്കെ, ദാറ്റ് ഇസ് ക്വൈറ്റ് തിയറിറ്റിക്കൽ. ഓക്കെ, കാരണം ബിക്കോസ് യൂണിവേഴ്സ് ക്യാൻ ബി കൺസിഡർഡ് ടു ബി കംപ്രൈസ്ഡ് ഓഫ് എ ലാർജ് നമ്പർ ഓഫ് ഐസൊലേറ്റഡ് സിസ്റ്റംസ്. Okay, subsystems ആയിട്ട് കരുതിയിട്ട് വേണം. So that is why we usually say that by comparing the entropy of isolated system or that of the universe, you will be able to predict which phenomena occurred earlier or later. That is why we usually say that entropy gives the direction of the arrow of time. So that's about the concept of entropy. We will be doing some problems also to calculate the change in entropy in different processes, which you have to practice much because in terms of your what do you say, the takeaway from the course, you should be able to do numericals. Okay, so one thing let me remind you that whatever equations that you have learned, see that you remember those equations along with its context where you have to apply. Okay, where you have to apply those equations, whether you have to apply it for an isobaric process, isolated system, for the universe, for a particular any system, okay, for adiabatic system, all those different differences between the topics, see that you understand. Summarize all those equations, and coming sessions we will be doing some problems also. Once you are familiar with the equations. Okay, so thank you.